In the previous video, we derived the rocket equation. It says that the change in speed of a rocket equals the exhaust speed times the natural log of the initial mass of the rocket plus fuel divided by the final mass of the rocket plus fuel for any 2 instants in time. Now, there's some engineering limitations to how fast you can make rockets go. And here's what they are. The best we can do for this ratio of initial mass to final mass is to get it to equal about 10. And the best we can do for the exhaust speed is have it equal to about 4,500 meters per second. That's for a rocket fuel that's combination liquid oxygen and liquid hydrogen. And when you use these 2 best possible numbers, you find that the highest speed you can attain is about 10 kilometers per second. And it turns out that that's not fast enough to send a rocket to the moon. You need about 11 kilometers per second to do that. So there's ways around it. The most common way is to use multi-stage rockets, where once a rocket engine has been emptied of fuel, it gets discarded, it gets ejected from the rocket, so you don't have to deal with the additional mass of the fuel containers. So we can get up to higher speeds than that by using multi-stage rockets. Multi-stage rockets have rocket boosters, and we dump those once all the fuel has been used up. How much force does a rocket engine provide? Well, we have a special name for the rocket force. We call it thrust. We use symbol T for it sometimes. So that will equal the rocket's mass times its acceleration, or m times delta v over delta t. Or m times the exhaust speed times change in mass over change in time. So let's analyze example 6.9. In this example, we've got a rocket with initial mass 10 to the 5 kilograms, burnout mass 10 to the 4 kilograms. It blasts off from the Earth, uses up its fuel in 4 minutes with an exhaust speed of 4,500 meters per second. And we'll figure out how fast it's going after it uses its fuel, how much thrust it's providing, its acceleration, and its speed, its maximum speed, if we include gravity pulling on it. So we've got initial mass of 10 to the 5 kilograms, a burnout mass, or a final mass after we've used all the fuel, 10 to the 4. Notice that's this 10 to 1 ratio that we were talking about. We'll use the good fuel, so we have an exhaust speed of 4,500 meters per second, and those engines are burning for 4 minutes. So the first question in this example is to calculate the speed at burnout, how fast the rocket's going after 4 minutes when it uses up all its fuel. So we just use our rocket equation. We say V final is V initial plus exhaust speed, natural log mass initial over mass final. Say the rocket starts from rest. We've got our 4,500 meters per second exhaust speed, and natural log mass initial over mass final is 10. And this gives us a final speed of 10.4 kilometers per second. All right, so how much thrust is being provided? Well, that thrust sorry, I shouldn't have included this M here. Thrust is the exhaust speed times delta M over delta T. And we can just plug in all our values. That gives us 1.69 times 10 to the 6 newtons of force. What's the initial acceleration of the rocket? Well, we can use our trusty Newton's second law method to figure this out. Sum of the forces on the rocket equals its mass times acceleration, and those forces are the thrust minus gravity force, mg. So the initial acceleration of the rocket will be the thrust divided by the initial mass minus g. .1 meters per second squared, which is it's a little less than 1 g worth of acceleration. And finally, let's return to this question of the final speed of the rocket, but this time include the fact that gravity is opposing its motion the whole way. Let's include the effect of the slowdown due to gravity pulling it. So the change in speed due to gravity pulling on the rocket will be minus gravitational acceleration times delta t, which gives you 2.35 times 10 to the third meters per second, or 2.35 kilometers per second. And we just subtract that from our speed we found earlier. So even when we include the effect of gravity pulling down on the rocket, we still get a really high speed that will be capable of sending this rocket into orbit.